So now may I invite Professor Zhou Hao. Okay, so Professor Zhou is from Nanjing University of Science and Technology in China, and his talk is about dislocation mechanism of HDI hardening in heterostructured materials. So Professor Zhou, please.
Play the video I sent you days ago.
Okay, maybe you can share your screen first.
Good afternoon, my dear colleagues. It's my honor to be able to give a talk in this high-level conference. My name is Hao Zhou. Now I'm working in the Nano and Heterogeneous Materials Center in Nanjing University of Science and Technology. Professor Yun Tianzhu is our director. In our center, most of the faculties focus their research fields on heterostructured material. First, I'd like to introduce our research group briefly. Our research center is located in the campus of Nanjing University of Science and Technology in China. Some of you may have been there if you attended these 4 meetings from 2014 to 2017. Now, we have built a professional lab of material science, especially in metallic materials. For example, we have processing machines such as rolling, rotational accelerator short penning, torsional extrusion, and rotary swelling. The latter 3 are designed for produce gradient structural materials. We also have a series of analytical instruments, including focus, ion beam, FIB, aberration corrected TM, and atom probe tomography. Moreover, some specific techniques such as in situ SEM, BIC, and TM are equipped for studying the microstructure evolution in real time. My team is working on in situ TM characterization, which is a powerful technique to study the dislocation mechanism during plastic deformation. During TM observation, we need a double-tiered stage because the best view of dislocation need to set a strict double beam condition. Moreover, if we want to get high-resolution TM images, the double-tiered holder is also necessary. However, until 4 years ago, there is no commercial double-tiered straining holder for in situ TM. So we use this bimetal strip to transfer heating to straining on the 652 double-tiered heating hold. Fortunately, in 2018, a new in-situ TM holder is launched by Bestron, a new company in China. They produce a double-tiered straining and heating coupling system. With this holder, we can perform stable in situ tension in TM at any temperature below 1000 C. Here is a new published work in Science. The atomic scale in situ TM experiment is performed using this new holder. We have also equipped this new system on the TM in our lab now. Next, I would like to introduce our members. Professor Zhu is the director of our center. He guides the main research direction and areas, for example, heterostructured materials. I have a team of institute TM characterization. We are working on the research of strengthening and toughening mechanism of heterostructured material. In my team, we have another associate professor, Li Xiao. She is very good at TM experiment, and these 5 young scientists, Guo Gao, Yi Liu, Meng Mingxu, Hao Zhou, and Jia Xihuang are my students. They are all working on the heterostructured materials now. The background of our research is based on a long-standing scientific issue. In our community, how to obtain both high strength and ductility is concerned by most scientists, even if they work on different metallic metals, for example, magnesium, steel, and aluminum. A big challenge can be described as this banana-shaped curve. The nanocrystalline metals usually have high strength but poor ductility, while the cold-grained alloy have high ductility but a low strength. How to break through this trade-off region is a big challenge in conventional homogeneous materials. Since 2015, the idea of producing a novel heterostructured material is proposed because we find a heteromicrostructure have potential to break through the trade-off of strength and ductility in different kinds of alloys. Here are 3 typical samples of heterostructured material, including laminate structure, gradient structure, and harmonic structure. All of these structures have 2 different zones, a hard zone and a soft zone. Moreover, the best distribution of them is not random. Some reports indicate that if a small amount of soft zone is completely surrounded by the hard zone, the mechanical property will be the best. The stress mechanism of heterostructured materials has been well addressed by the theory of HDI hardening. The main reason for heterostructured material to keep a good ductility and a high level of stress is contribute to high strength hardening rate of the whole system. It has been proposed that the GNDs high up at the interface of the soft zone provide additional strength hardening effect. Meanwhile, a forward stress with the inverse direction in the hard zone can reduce the critical flow stress for its plastic deformation. Therefore, the forward stress promotes the plastic deformation of the hard zone. The HDI hardening has been intensively investigated. For instance, the GNDs high up at heater interface are found by EBSD experiment. This result indicates that the proposed back stress in the soft zone is achieved by additional work hardening of GNDs. And our research is to explore the detailed evolution of GNDs and reveal the dislocation mechanism of the HDI hardening. The main difference between heterostructured material from homogeneous structural material is whether they are heterointerface. We also define this interface as Zoom boundary. Thus, the most important thing when we investigate the physical mechanism of HDI hardening is to obtain detailed microstructure evolution nearby these heterointerface. There are two scientific issues need to explore in this research. First, where is the location of GND source? This is an easy confused question because GND are defined as a kind of dislocation to accommodate bending or internal plastic strain gradient in conventional homogeneous metals. In the heterostructured material, the GND usually form nearby the heterointerface to accommodate the plastic incompatibility. We use a regular copper alloy with lamellar layers to investigate this mechanism. The sample for in situ TM experiment are obtained from the copper alloy sheet produced by ARB. The pure copper and the boron layer are staking one by one after rolling. We know the required sterilization temperature of pure copper and the boron are different. So, if we anneal the cold-rolled sheet at a temperature between them, the pure copper layer will be well annealed and obtain a coarse-grained microstructure. In contrast, the required sterilization in boron layer doesn't happen under this temperature, and its microstructure is still nanocrystalline. We use FIB to lift a sandwiched boron copper sample for in situ TM observation. As shown, the tensor direction is parallel to the heterointerface between the pure copper and the boron. In the following slides, I will show you the movies in all the stages of tensor deformation. At the beginning, we find some local strain concentration at the interface. We can see the changing contrast in this area. After a short time preparation, interfacial dislocation source is activated at this position, start to image the dislocation. We found that most of the dislocation image from this interfacial source are partial dislocations. A nanochain is formed by continued emission of partial dislocations. In addition, Frank Reed source are also activated in the grain interior in this stage. If we count the number of dislocations, we will find that the Frank Reed dislocations are dominated during the tensor deformation. The dislocation slip towards the heterointerface and finally high up there. Note that this observation is consistent with the proposed mechanism of backstress strengthening. In most post-mortem TM experiments, people find high-density dislocations high up at the heterostructured interface. However, the high-resolution DIC analysis on the same sample raise different questions, difficult questions. Looks here, the strain at interface are much higher than green interval. We know if the dislocation are emitted from Frank read source in green interval, and finally high up at the heterostructured interface, the strain at the interface should be lower than green interval. So the TM results looks contrary to the results obtained by high-resolution DIC. As the in-situ straining experiment continues, we find some dislocation will be pinned in the matrix. The spots could be jogs generated by the interaction between dislocation. Looks here. Once the dislocation XY interact with dislocation AB, a dislocation segment P prime will be formed. Because the Burgers picture and the dislocation line are not in the same slip plane, the PP prime is an immovable dislocation, and the two edge arms can behave as single-ended source. Once two jogs are formed in the same slip plane, a new Frank reader source will generate. On another side, an activated source could also be deactivated if a new jog forms on the dislocation segment between the two pinning spots. Because the critical shear stress to achieve activate dislocation is inversely proportional to the length between A and B. So the Frank reader source are dynamic activated and deactivated during the deformation process. Without an in-situ TM observation, we can hardly obtain this evidence. We observe at least 10 different Frank reader sources successively appeared in this region. And as mentioned above, the activation and the deactivation of dynamic Frank reader source are result from the interaction between the dislocation with different Burgers filter. We also find Frank reader source, Frank reader dislocation interact with the twins image from the interface. It can be seen that some dislocation leap in the inverse direction of the twinning partial. When the dislocation line interacts with the twin boundary, they will cross-leap onto this twin, and there is little influence on the Frank reader source. Now we can answer the question raised above. why the strain at interface is higher than in grain interview. The statistical result shows that there is a density gradient of dynamic Frank-Reed source. The density of dynamic Frank-Reed source decreases with the increasing distance from the interface. Therefore, in DIC analysis, the mapping shows a highest strain at the hetero interface. The second scientific issue is how the GNDs interact with interface. We select a dual-phase high-entropy alloy, which contains both hetero interface and regular grain boundaries for comparing. The alloy contains 5 principal elements, including aluminum, cobalt, chromium, iron, nickel. After rolling and annealing, we get a dual-phase heterostructure, where the BCC and FCC phase are shown in brown and blue in this map, respectively. There are 2 different interfaces in the microstructure. One is the phase boundary. Between BCC and FCC. The phase boundary is a typical hetero interface because the hardness of FCC and the BCC phase is very different. Meanwhile, the second kind of interface is grain boundary in FCC grains. The grain boundaries are not hetero interface because both their sides are FCC grains, which have a same hardness and yield stress. The mechanical property also show a high HDI hardening effect in this alloy. We use loading, unloading experiment to test the HDI stress. The stress strain hysteresis loop is the sign of HDI hardening effect. Also, we found a significant increase of HDI hardening with straining in this HEA material. The dislocation behavior in the HEA is different from conventional metals and alloys. For one thing, the dislocation source in HEA are mostly on the interface. For another, the dislocations are restrained in some specific slip planes, forming such a kind of slip area. Moreover, we found that once the leading dislocation in the area are blocked by something, the following dislocation will cross-slip to other planes as marked by the red arrows in this image. To investigate the interaction between dislocation with interface, we conduct in situ TM near a grain boundary first. We know the grain boundary is not a hetero interface in this area. We find the GNDs encounter a grain boundary building up a local strand concentration. The leading dislocation is suddenly absorbed by the grain boundary. At the same time, dislocation are emitted on both sides of the grain boundary. It can be concluded that dislocation could transmit through the conventional grain boundaries, possibly by the reaction between incipient dislocation and the grain boundary to form a new dislocation on the other side of the grain boundary. However, the dislocation behavior at face boundary, also zone boundary, is very different. We can find high up and the reflection of dislocation at face boundary. Moreover, the dislocation reflection happens consecutively between the opposite face boundary, forming a zigzag trace. We also find that such reflection is achieved by cross-sleeve of screw dislocations. We know most reflection of GND area occur at the zone boundary. However, the zone boundary are not parallel to the Berg's picture. Berg's picture of dislocation. Therefore, the leading dislocation acts as cushion at the zone boundary, providing a buffer layer to adjust the angle theta between the Berg's picture and the zone boundary. These GNDs exert an expiring force to the income GNDs. Okay, here. Maybe a GND number 4 may experience enough driving force to align a segment of this dislocation line parallel to its Berg's picture, and thus to able cross-link onto the reflection plane. The cushion dislocation leaves near the zone boundaries, no doubt to increase the dislocation density at these positions. A compared statistic data shows that the dual-phase structure in high entropy alloy have higher HDI hardening rate than in other dual-phase alloys. This could be result from the multiple reflections of GNDs at zone boundaries. Come to the conclusion. We have answered the two questions raised at the beginning. We find a kind of dynamic Frank-Reed source in grain interleaving. They are the primary dislocation source of GNDs. And high up the GND in dual-phase HEA reflected from the hetero interface consecutively, producing high-level HDI hardening rate. And that's all of this presentation. Thanks for your attention.
Okay, thanks, Professor Zhou, for your talk. Now, let's see any. Okay, we've got two questions. So the first question is about: is there any difference between the transmission and the absorption of a dislocation by the boundary? Professor Zhou.
Okay, thank you, Professor. We find two kind of dislocation reaction at interface. One is grain transmission. Transmission is on the grain boundary, and another is reflection at a grain boundary. The difference between transmission with what? Absorption?
Yeah, they ask absorption of a a dislocation by the grain boundary.
The observation happened before the transmission when the leading dislocation encounter with the interface, and it's first absorption by the interface, and then new dislocation source at interface is activated and start to image dislocations towards both sides of the grain boundary. So it looks like the dislocation transmission the grain boundary. But in my opinion, I think there are two steps. One is observation, and the next is a new dislocation nucleated, new dislocation source nucleated at the interface. Thank you.
Okay, so the second question is on your slides 31. Yeah, when cross slip improve the strength hardening of the HEA, does this affect the HDI strengthening due to affected GND pileup formation? So it's on your slides 31.
Oh. On my slide 31 is dislocation cross slip at in-grain interior. This is the unique phenomenon in the high entropy alloy. When the dislocation encounter with the phase boundary, zoom boundary, it will reflect it. However, if the dislocation slip in grain interior, once it when it's the leading dislocation is blocked by maybe another slip plane, then cross slip also happen, and I think this cross slip will increase the slip dislocations in the grain interior and increase the dislocation density in the grain interior. So it will be helpful for the strength hardening sense.
Okay, so the last question. So Professor Zhou, the phase boundary is a coherent boundary according to the EBSD?
The phase boundary may be, I don't think the phase boundary is a coherent boundary. We conduct a high resolution TM, and we found one way side of the grain is on a zoom axis. Another side is far away from the low index axis. This is the first thing. Another thing is from our EBSD mapping, we find the ECC grain have a same orientation. The color, we can see the color is green, and the FCC grains have many orientation. So we can infer from this phenomenon the phase boundary could not be a coherent boundary. Thanks.
Okay, thank you. Any other question? from the audience online? Okay. So if no further question, let's thank Professor Zhou again.
Thank you.
Thank you.